Okay, so last time we talked about the work sharing construct for OpenMP, and we have introduced four as example, and we will talk about sections and single today. Okay, and for the four construct, right, we introduced the scheduling clause before the end of the class last time, and there are a few other clauses, right, that can work for the for directive. One of them is order. We briefly introduced it. It's a clause that force the result. The thread needs to be the completion order of those threads needs to be the same as the sequential code. Okay, so during the process, those threads still be executed in parallel and without any specific order. But you can imagine it will have introduced a lock at the end. So it will force the threads to finish in the same order as the sequential code. Okay. And of course, this will greatly reduce the parallelism and introduce significant synchronization overhead. So normally we don't use it, but in some cases we need it. So OpenMP still support this clause. Okay, and the last one is the collapse. Okay, we mentioned this is only work for nested for loop. Okay, and the requirement is that all the for loop you're going to collapse basically means flatten or merge together. They need to be written consecutively, like over here. So you cannot, for example, have the clause. You cannot have a for sit between those two compiler directives. Okay, you have to have all the for loops over here before you call the collapse. Okay, and the purpose is to flatten the iterations. So it should only be used if your inner and outer for loops they don't have any dependency, right? For example, over here you have I and j, right? Two loops. Okay, and if you flatten, you will see those, right? 4x4 iterations, right? And if no, you have if you don't have a collapse, okay, then the threads created for this pair region will be only parallelized at the first loop. Basically, that means for I. Okay, so since here you have only only have 0, 1, 2, or actually it's 3x3, right? So it's only have 3 iteration for the I for I. Then even though you have 6 threads over here, right? Only 3 of the threads are active, right? Because you only see this for loop. It can only be parallelized at this first level. Okay. But with collapse, here you can indicate how many layers, right? How many, because you could have I, J, and then K, right? So on and so forth. So you can control how many layers of iterations to collapse together. Okay. And here, because you have 3x3, so in total of 6 tasks, right? So after flatten them or collapse those 2 iterations together, you can distribute those 9 tasks to those 6 threads. So you can see like the example shown here. Okay, and we said you shouldn't have data dependency between those 2 iterations because obviously you can see the execution of for the inner loop will also be shuffled, right? You will just be flattened and executing in no particular order. Okay, so for example, if your result from a equal to 0, I equal to 0 must be computed before the iteration of I equal to 1, then you shouldn't collapse those 2 iterations together. Okay. All right. So you need to be more careful about the data dependency between those loops. Okay. All right, and that's it for the for loops. Okay, And the next one is sections. So the section, as we mentioned, is a way to distribute the computing, is to distribute it at the code level. So the way to use it is as shown below. You will have a directive for sections, and within the bracket you will write the code for each section. So each section is a single task, and it will only be executed by one of the threads in this parallel region. Okay, so you can make sure all the sections will be executed, but they will also only be executed once by a single thread. Okay, and of course the mapping between the section and the threads again is decided by a scheduler. But in this case, there is no scheduling option for the programmer, because usually, as you can imagine, the programmer shouldn't write too many sections, right? In this case, maybe 10 section probably is already a lot, right? As for a programmer, so the number of tasks shouldn't be too many. So how is it get scheduled doesn't really matter too much. But anyway, it's controlled by the library automatically. Okay. And here just a quick example, right? So again, you can define many section of code. And remember here, it's only under a section directive, not the for loop directive. So even though here you have a for loop, it is not parallelized. It will be executed by a single thread in a sequential way. Okay, right? And so that's basically how we use sections. Okay. All right, and the last one is single. So as we mentioned, it's kind of a special case for synchronization or coordination among the threads. And its purpose is to only allow a single thread to execute a piece of code in a parallel region. So for example, over here, right, only want one thread to read the input and then maybe ask all the rest of the threads to process the data. So you will put this data reading statement inside a single region. Okay, so that will force only one thread execute that statement. Okay? And again, by default, there's a implicit barrier at the end of this single region. So all the threads must be wait until one of the threads execute this scaf statement. Okay? And again, you have the no wait clause. You can add it after, in this line after single to allow those threads without be blocked by this single region. Okay, so whether there's a barrier or not can always be controlled by the programmer. Okay. All right, so you probably can imagine, right, some of the use case you will want to use single so you don't need to jump back and forth between parallel region and just sequential code region, because if you exit a parallel region, that means you call a join on all the threads. So those threads will be terminated, right, and forced to join the main threads. So that means you will have more thread creation and deletion in your program. So if it's just a temporary, right, temporary and just few statement need to be forced on a single thread, then you should use single. That could be more efficient, right? That can make your code run more efficiently and avoid too much thread join and fork statement. Okay. All right, so that's pretty much it for OpenMP. So you can see the compiler can only help you on certain pattern, and but those if you have those kind of code, if you get parallelized, you can achieve pretty good scalability, right? So that's why many people would like to use OpenMP, try to parallelize their code first, and see if the program really can benefit from parallel computing. Okay? If you observe those benefit, then of course you can, if you want to refine your code to further make the parallelism more efficient, then you can write your own thread version, right? Okay, so lastly, the construct will introduce is for synchronization, similar to single actually, but of course here is more, as you can see, it's more closer to some of the synchronization tool we introduce in pthread or for thread programming. Okay. And the directive for synchronization, including master, critical, barrier, and atomic. It shouldn't be too hard to understand, right? The master is basically the same as a single directive. But the difference is actually the threads we create, there's one specific thread is called the master thread. So if you use master directive, the compiler will make sure that piece of code will only be executed by the master thread. Well, if it's just single, then the compiler at the runtime, it will just pick one of the threads, probably whoever reached that statement first to execute the code. Okay. So what's the difference? The difference is, for example, if in a parallel region, right, you want to some code execute by a single thread in multiple places, and if you have two single directive, you cannot guarantee it's the same thread to execute the code. But if it's use master directive, then you can sure master thread, it will be the same thread to execute for the both piece of code. Okay, so of course that means, right, some of the memory state can be reused throughout the execution, something like that. So anyway, you can imagine some case you do want to force specific threads to handle all the, for example, IO operation or something. Okay, in that case you should use master. Okay, because single cannot guarantee you which thread to execute the code. Okay, all right. And the critical is exactly like critical section. Okay, so by definition, that means only one thread execute at the time. So different from single, with critical, you still have all the threads enter into this section and execute the code, but they will be executed one by one. So it's a way to force serialization among threads, right, inside a parallel region. Okay. And barrier, of course, is sent as just a barrier code. Okay, so you will basically just block. It's just the same as the barrier API you code in MPI program. Okay? And finally, it's atomic. Okay, and atomic, you can think it as the statement level synchronization in Java, right? As we mentioned, basically the compiler will analyze your memory reference to decide when to introduce the lock in your code. So compared to critical, atomic is a more fine-grained lock in your parallel region. Okay. All right. So that's some of the option you have for addressing the synchronization problem. Okay. And of course, OpenMP, it can be used with other, especially those thread libraries, like the mutex lock or critical section condition variable. All those functions you can still code it with the OpenMP code, right? But if you are using lock, it will be recommended to use the lock provided by OMP to avoid some of the maybe library confliction or dependency problem. Okay, so OMP, it does provide the locking API for user as well, just like the mutex lock within from pthread library. Okay, I think all of you should probably familiar with those API now, right? You need to init, destroy, and set is a lock, right? Unset is unlock, right? And it also provides text, so you can check whether the lock is already acquired by other threads already. Okay. All right. So it's recommended if you want to use lock, you should use the lock from OpenMP if you are doing OpenMP programming. Okay. And here just the example for right how you could comparison. You can use critical section, you can use atomic, or you can just call the lock and unlock function code. Okay. Of course, performance-wise, they could be has some differences, but the programming logic-wise, you can choose either of them in your implementation. Okay. All right. So finally, actually, we're going to talk about the most important part for OpenMP. That's the clauses for manage the data scope of your variables. Okay. And it's important because sometimes it could be confusion, right? Because the actual code from your program is generated by compiler. So you actually have to imagine, or you have to configure the compiler, right? To know, depends on your configuration, then the code generated will be different. So you have to know what's the how this configuration will affect compiler, so you can imagine what the code will actually looks like. Okay, and one of the confusion point is certainly be the data scope of a variable, right? Because the variable you define in a program or you write in your program will be moved to a function code. And so when it moves to a function code, then you can decide, you have to decide whether it's just a local variable or it's actually a reference to a global variable, right? And of course, those two have different data scope. So this is actually control. Well, there's a default decision made by the compiler, but the programmer can also overwrite that setting using some clause. Okay. So first of all, the data scope in general, what we need to distinguish is whether the data, the variable, right, is a global variable or local variable. Or in this case, whether it's a shared memory, right, among the threads, or it's just a private variable to a single thread. Okay, so you can see by default, okay, actually those variable by default, any variable you think from the code should be a shared variable. Okay, but it will be converted to private only for a certain cases. Okay. So one of it is that if no, okay, so I should say most of the share, right, including everything, and of course, if you have static or from your program, you already it's a dynamic allocate variable, then obviously they are share, right? But for private non-share variable, it will only happen for some cases. Okay. So one of it is it's a variable for the loop index, right? Like the for loop, in a for loop iteration for I, for j, for k. So I, j, k, they are private variable to each of the threads. Okay, it's not hard to imagine, right? Because obviously, this is the reason why each thread can run on different iteration, because their index, right, is different. Okay, so by default, those variable will convert it into a private variable for the thread function. Okay, and secondly will be the variable that you declare inside the parent region. Okay, so if you declare inside the inside the parent region, will be like you declare a variable inside a function call, right? So of course, it will result in a private variable, a local variable. Okay. So as you can imagine, most of case they are shared. Okay. But for your programming purpose, as we will see a few example, in some cases you actually want to that each thread has a their private variable. Then you can override the scope with the clause we introduce. Okay. And the clause, basically the clause you need to know are all listed over here. Okay, so you can see there's a private, share, first private, and last private. So those four are usually the clause we use to override the data scope or specifically specify the data scope of a variable inside a parent region. Okay, so let's just look at the definition. Okay. So private, obviously, that means whatever the variable, right? So you can see after this clause, you have an argument. So you can have a list of variables over here. Okay, and the variable listed over here means that the compiler will know that when he generate the function code, right, from your parent region, when he encounter those variable, then he will declare, right? Well, we will create this local variable for your inside the thread, inside the function. Okay, so he will know that he need to create a declaration for this variable. Okay, and as you can see over here, however, the compiler or the code does not tend to initialize the value. It's only try to declare the variable. Okay. And so, of course, that's a default. Usually what happens, right? After we declare, we should, if we want to initialize it, we should initialize it by some specific or explicit statement, right? So same thing here. By default, it's not initialized. It's only allocated, okay, and allocated as a local variable, okay, inside a function, okay, for a thread. Okay. On the other hand, share. Okay, so share means that you will, of course, if needed, he will declare the variable, and you will declare as a reference only. Okay, so you will actually allocate the variable, as a global variable, and pass the reference to all the threads. So all the threads can access that share variable. Okay, so this is the way that you can override the data scope to share. Okay, as a global variable. Okay, all right. And what's first private? So first private usually used with basically first private and last private. They are both used with a private variable. But besides declare a private variable for first private, he also tried to initialize the variable. Okay, and the value initialized will actually depends on whether the variable has been used before you enter the parallel region. Okay, so we will show a code in the next page so you can see what that really means. Okay, but anyway, it is used for the case if you try to initialize the same value for all the threads. Okay, remember it's a private variable, so they are actually different variable for each thread. But if you want to initialize them to the same value, initialized value, then you should call first private. Okay, and the last private is used when you exit the parallel region, right? Because imagine, right, in the parallel region you have 10 threads, and is a private variable. So that means each thread may hold their own value for that variable. But after exit the parallel region, only one thread remain, right? So you have to decide which one, right? The value from which thread should be remain, right, or to keep. So the last private will make that decision, and the decision is simple. The decision will be the value will determined by the last thread to exit the pair region. So basically, you will keep override the value until all the threads are terminated, okay, or join the main threads, okay. So let's look at the example code will be more clear, right? So you can see over here in the example above, right? If we only call private, okay, if we only say private var1, then the print result is unknown. So the var1 can be any value because var1 is not initialized, okay? And every thread may print out different value because they may get some random numbers, okay? But if you have a first private, then the compiler will check, right? To check whether, before you enter this pair region, whether this variable with the same name is declared. If it's declared, then he will check the value. He will use the value for that variable and copy that into for each of the threads, okay, in order to initialize those local variables, okay. So in this case, because we have the first private and we actually do initialize the value for var1 before we enter into the pair region, so we should expect all the threads to print out 10 in this case, okay. So as you can see, just a way to just like you call right, a scatter, right, before you do any computation, okay. All right, so and for last private, as we mentioned, again, just like the inverse of first private, last private define the value of a private variable or a variable after you exit the pair region. So in this case, you can see the value for var1 depends on your thread ID. So everyone has a different value for var1, which is a private variable. So it's fine. But after you exit the pair region, then if we do want to copy the result from the thread to the main threads, the worker thread to the main threads, then we can use last private to do that copy, okay? And we will copy the last one. And here, the sleep time depends on the thread ID as well. So we should expect the largest thread ID will be printed or assigned to var1. Okay. All right. So pretty much like gather and scatter, right, in MPI program. And here we have first private and last private to do a similar thing. Okay. Okay. And by the way, remember the var1 over here, right? It's belong to the main threads, right? And here, although we don't declare var1 in the pair region, but because var1 is a private variable, so by default, the code generated from the compiler will add that variable declaration in your function, right? So the var1 outside the pair region and inside the pair region, they are different, okay? So that's why you have this clause to decide what's the relation of their value between those different variables you created, okay? All right. And so the last one is default, right? So default means you will override for all the variables, because sometimes in your function, the function inside your pair region have too many variables, and you want to decide their data scope at once. Then you can use default. Okay, so you will override everything except for the for loop index. Okay, that's always to be private. Okay. Okay, and copy in. Okay, copy in will only be used. It can only be used or have effect if it is used with the master directive. Because as you can see, the purpose of this one is that you will try to copy the value from the master thread to all other threads inside a pair region. Okay, so usually it will only have meaning if you have this with the the master directive, right? Because only the master thread will execute the code inside a master directive. And if you want to copy that result to all other threads, um, then you can use copy in, right, as the clause follow the master directive. Okay, so that means you will copy the result out after you exit the master directive region. Okay. Okay. So similarly for single directive, we have this copy private. It's basically exactly the same as copy in, but just right one for master thread, the other for single directive. Okay. And finally is reduction. So reduction is try to as we have introduced in MPI program, right? Reduction is try to aggregate the result from all the threads or processes. And in this case, of course, you will try to have the reduction when you exit the parallel region. Okay, so if you want to collect the result and use some operator to aggregate the result after you exit the parallel region, then you can specify the reduction clause, follow your parallel region. Okay, follow your parallel directives. Okay. All right, so we can see a quick example over here, right? So for example, here we try to, as you can imagine, we try to compute the total sum from this array, right? And so you can see here the result is a private variable, okay? And oh, by the way, of course, the variable for reduction clause also means it will be private. Okay, at least it will be private inside the parallel region. And usually we expect the variable is actually defined outside the parallel region. So that's why we can copy the result from the within the parallel region to the variable outside the parallel region, right? So we can get the aggregated results without just simply overwriting them. Okay. And here the result must be private because you can imagine all the threads, right? They try to do some operation and override the result variable. So if the result is a shared variable, then you have a race condition. You have, right? You shouldn't allow all the threads operate on the same on the shared variable at the same time, right? So that's why the result should be a private variable. Okay. But after you exit, you will want to aggregate the result back to a single variable. So that's why you can use reduction to do that. Okay. So it's a way to collect the result from all the threads, basically. Okay. All right. So that's the last class we're going to introduce. Okay. Right. So of course, there are more clauses can be used from OpenMP. And here is a summary for the clause we introduced. But importantly, you will see that not all the clauses will have effect on all the directive, right? Depends on the combination. Okay. So some of the clause will only apply on certain directive. Okay. And if it's not applied, it's unchecked over here, that means it will be ignored by the compiler. Okay, so you will have no effect to your code at all. Okay. This is just a reference for you for when you do the programming, and of course you can check out the API reference to find out more. What are other clauses you could use for each of the directive? Okay. Right. So finally, this library is a routine, right, from the OpenMP library. And as we mentioned, there are not too many routines provided by the library because programmer mostly is to do the MPI OpenMP programming using the compiler directive, not using the library. Okay. But we have seen the library for synchronization, for at least for lock and unlock, right? And also there are a few other library code you could use to find out, for example, how many threads are there, or to set the default value for number of threads, right? We introduced that before. And also you can query the library to know what's the maximum number of threads you can use on your machine or in your program, or the number of processors on your machine, right? So you can determine what should be the better setting for your thread number, okay? Or you can use imperial to check whether your code is currently inside a pair region or not, etc. Okay. All right. So that's the purpose for those library routines. Okay. Okay. So that's it for the OpenMP. And for this class, you basically only require to use those very basic directive from OpenMP. We actually don't have a single homework assignment for OpenMP alone, right? Instead we ask you to use OpenMP with maybe GPU programming with MPI in our homework. Okay, and you will see that one of the most important class you need to use and also conduct some experiments on is the scheduling class. Okay, so we want you to see how the dynamic scheduling and static scheduling will affect the performance in our homework too. Okay. Okay, so that's it for the OpenMP. Okay, we have a few minutes left, but I think we can reserve that time for some questions. And if we don't have questions, then we can finish the class today earlier, and we will start move on to the next phase of our lecture. We're going to talk about the parallel computation or parallel algorithms like pipeline, divide and conquer, and we will also we will use many simple application as example to show you how those parallel algorithm can be implemented or applied to solve those problems. And of course, through that, we will introduce the application you're going to implement it for your homework 2 and homework 3. Okay. All right. So that's it for today's class. So any questions? Feel free to raise your hand. You can even ask in Chinese. It's perfectly fine.